Hello everyone, I'm Mr. Tan and you are watching Chemistry Tutorial. Now this is the first time I'm doing a live stream, so I hope you enjoy it. Now, in this live stream, we will be going through the Cambridge International Exams, CIE, AS and A-Level Paper 1 multiple choice questions. I'll be going through all the 40 MCQ questions. This paper was set in February, March 2018 last year. Now let's begin. Question 1. Now I've actually highlighted the answers with yellow so that you'll be able to know what is the answer for every individual question. But I'll be going through all the questions in detail. Now, question 1. What are the shapes of the molecules of water and boron trifluoride? Now to do this question, you need to know the Lewis structure. Now I don't encourage you to draw the dot and cross because it's very time consuming. So for water, now I need to identify which is a central atom, which is oxygen in this case. Oxygen is in group 6, or sometimes people call it group 16. I prefer to call it group 6 because it's easier to remember the number of valence electrons, because group 1 has 1 valence electrons, group 2 has 2 valence electrons, group 3 has 3 valence electrons, etc. So oxygen is in group 6, so it will have 6 valence electrons. So therefore for this case here, it will have 2 lone pairs. Now, so it has 4 electron region. You have 2 bond pairs and 2 lone pairs, which means that its basic shape is tetrahedral. However, we are interested in the molecular shape. Therefore, this water molecule has a band shape or a V shape. Definitely not linear. Therefore, option A and B are out. Now for BF3, boron is our is in group 3, is our central atom. However, boron doesn't have any lone pairs, which means that its basic shape is the same as the molecular shape. In this case, it is trigonal planar with respect to the central atom, boron. Therefore, for this question 1, the answer is D. For question 2, the electronic configuration of the 2 outermost shells of an atom is 3s2, 3p6, 3d5, and 4s2. Now, if you see the subshell, the D subshell, that means that this is a transition element. Since we know that this is a transition element, therefore phosphorus and strontium can be ruled out because phosphorus is in group 5, strontium is in group 2. So the answer could only be manganese or vanadium. Now let's have a look at our periodic table. My periodic table looks a little bit small, so you may want to use your periodic table instead. Now, as you can see here, this is your S block. This is your P block. The central one is your D block. The last 2 rows is your F block. So now 4s2, which means that in this case here, so period 1, period 2, period 3, and period 4, so 4s2. But 3d5, which means that 1, 2, 3, 4, 5. So hence, the answer for this is manganese. Now, question 3. Drinking water may contain calcium hydrogen carbonate. How many electrons are present in a hydrogen carbonate anion? Now, the molecular formula of hydrogen carbonate is HCO3 minus. So, just for information, if the question ever asks you how to draw the Lewis structure of HCO3 minus, it will look something like this. With the oxygen atom carrying the negative charge, this oxygen itself is actually a band shape with respect to this oxygen atom and trigonal planar with respect to these carbon atoms. Now, for hydrogen, it's 1, 1 hydrogen. Carbon is 12,6 carbon. Oxygen is 16,8 oxygen. Now I put in a mass number at the top. However, due to the change of syllabus, there are some periodic table that actually put the mass number at the bottom. It's okay. Just choose the bigger number. The bigger number will be the mass number. So the question is asking about the number of electrons present. So for electrically neutral species, for example, an element, an atom, the number of electrons is the same as the number of protons. So for hydrogen, you have one proton, which means that hydrogen actually has one electron. Carbon, you have 6 protons, which means that carbon has 6 electrons. Oxygen has 8 electrons, 8 protons, so therefore it's 8, but you have 3 of them, so you have to multiply by 3. So it's 1 plus 6 plus 8 times 3. However, the hydrogen carbonate actually carries a -1 charge, which means that you have to add in 1 more electrons. So 1 plus 6, 7, 7 plus 24, you get 31, 31 plus 1, and you will get 32. So answer is option C. Next, for option D, which molecule contains a nitrogen atom with sp hybridized orbitals? Now let's go through all the options. CH3, CH2, and NH2. I'm going to draw the lone pair in as well. Now, to know the hybridization state of every individual atom or element, you need to know its basic shape. So the basic shape with respect to nitrogen is actually tetrahedral because you have 3 bond pairs and 1 lone pair. So the hybridization state that's associated with tetrahedral is sp3. So how do you remember that? Well, just take it that you have a 1s and 3p, so you have 4 electron regions, so tetrahedral, so sp3. Right, this is the shortcut to remember, remembering the hybridization state. HNO3 is our nitric acid. You have to be able to draw the Lewis structure of nitric acid. So nitrate looks like this. NO3 minus, nitrate looks like this. But because it's a nitric acid, so a proton is gained. Hence, for information, the molecular shape with respect to oxygen is actually band shape because this oxygen has 2 lone pairs and 2 bond pairs. And the molecular shape with respect to nitrogen is trigonal planar. Now, because there's no lone pairs, that means the basic shape is the same as the molecular shape. In other words, it's trigonal planar with respect to nitrogen, and hence the hybridization state is actually sp2 because 3 electron regions, so it's like 1s and 2, so 1 plus 2 is 3, so sp2. So option A and B are not correct. HCN. So for nitrogen itself, there are 2 electron regions. Now, although this is a triple bond, we still consider it as a 1 electron region. So 1 electron region, 2 electron region, so sp hybridized because 1 plus 1 is 2, so 2 electron region, sp hybridized. Therefore, the answer is option C. But we have a look at option D as well, which is ammonia, NH3. Now, nitrogen is in group 5 or group 15, but as I mentioned earlier, I prefer to call it as group 5. So it has 5 valence electrons. So there are actually 4 electron regions surrounding the nitrogen atom because 3 bond pairs, 1 lone pair, which means that its hybridization state is sp3 because 1 plus 3 gives you 4. Therefore, option D is not correct. Now, for question 5, okay. Now for question 5, which mass of solid residue is obtained from the thermal decomposition of 4.10 grams of anhydrous calcium nitrate? So we need to know the equation. Calcium nitrate, CaNO3 undergoes thermal decomposition to produce calcium oxide plus nitrogen dioxide, but you have 2 moles of nitrogen dioxide, it's a gas, plus half a mole of oxygen. Calcium oxide is a solid. In this case, our calcium nitrate is also solid. So now, based on this is a balanced chemical equation. So 1 mole of calcium nitrate produces 1 mole of calcium oxide, and this is our solid residue. So first, we need to determine the number of moles of calcium nitrate by using the formula mass over mR. So the mass is 4.10 grams over the mR of calcium nitrate. So you have to refer to the periodic table for their respective AR. So for this case, I'll just take the AR of calcium as 40, although in some data booklet they put as 40.1, but it's okay. 40 plus 2, because you have 2 nitrogen ion. AR of nitrogen is 14. You have 3 oxygen atom, and the AR of oxygen is 16. So, and the answer is, try to work this out by yourself as well. And the answer is 0.025 mole. Now, based on the chemical equation, the stoichiometric ratio of calcium nitrate to calcium oxide is also 1:1, which means that the number of moles of calcium oxide is also 0.025 mole. Now, the question is asking us for its mass. So we have to use a formula. Number of moles is mass over mR. But in this case, the mass will simply be mass equals to number of moles, which is 0.025, times the mR of calcium oxide, which is 40 plus 16. So press your calculator, the values. And the answer is 1.4 grams. Hence, option C is our correct answer. Now, let's move to question 6. Now, for question 6, sodium hydroxide neutralizes acid. So H plus plus OH minus give you H2O. This is the ionic equation that represents any reaction between an acid and a base. So in a 11,000 dm³ sample of an aqueous solution, the concentration of acid H plus is 1.26 times 10 to the power of minus 3 moles per dm³. Which mass of solid sodium hydroxide neutralizes the acid? Now, first, we need to determine the number of moles of H plus ions by using a formula concentration times volume. And the concentration given to us is 1.26 multiplied by 10 to the power of minus 3 multiplied by the volume, which is 11,000 dm³. So the dm³ units will cancel off each other. So let's key in the values. And the number of moles of H plus ion is 13.86 moles. Now, based on the ionic equation, the stoichiometric ratio of H plus to OH minus is also 1:1, which means that the number of moles of hydroxide ion is also 13.86 moles. Now, sodium hydroxide itself is a strong base. So sodium hydroxide itself will dissociate completely in water to produce Na plus aqueous ion plus OH minus aqueous ion. Which means that the number of moles of sodium hydroxide is also 13.86 moles because it's 1:1 ratio. Now, the question asks us for its mass. Hence, we use a formula. Number of moles is mass over mR. So mass is the number of moles multiplied by the mR. So the AR of sodium is 23, oxygen is 16, hydrogen is 1. So 13.86 multiplied by the mR of sodium hydroxide, which is 40. And this is our mass, which is 554.4 grams. So we choose the best option. In this case is option D. Now let's look at question 7. Now for question 7, the gas laws can be summarized in the ideal gas equation, PV equals nRT. The P stands for pressure, and it has a unit of Pascal. V is our volume, and it has a unit of meter cube. N is our number of moles. R is our molar gas constant. Now, depending on whether you are taking physics or chem, the R value could be different. But for chemistry, our R value is 8.31 joules per mole per Kelvin. And sometimes it's also known as the universal gas constant. T is our temperature in kelvins. Now, in order to use R as 8.31, you must make sure that the units of P is Pascal, the units of V is meter cube, and the units of T, the temperature, is Kelvin. Now, using the formula, PV equals nRT, the question is asking us for the pressure. Therefore, we can make P, the pressure, our subject. So P is equals to nRT over V. The N is the number of moles of oxygen, which is mass over MR. So 0.960 over the MR of oxygen is 16 times 2, because the AR of oxygen is 16 and we have 2 of them. R is 8.31. Temperature must be expressed in Kelvin. So therefore, 273 plus 30 over the volume, which is 7.00 times 10 to the power of minus 3. So key in your values and let's work out the answer. So the answer is actually 10791 Pascal. So out of these 4 options, only option C is the most reasonable one, because you can actually approximate this to 10800 Pascal, which is equivalent to 10.8 kilopascal. Now let's look at question 8. Let me scroll it up. Now, for question 8, this is a definition question. Which equation represents the standard enthalpy change of formation of water? Now, the key thing that you need to realize is that for the formation of water, water is our product. So therefore, the actual definition goes something like this. It's the energy change when 1 mole of the product, in this case water, is formed from its constituent elements at standard conditions. So our standard conditions refers to our 25 degrees Celsius. Now, since we need to form 1 mole of the product, that means options C and D are wrong because they produce 2 moles of the product. So the remaining options that we have are A and B. Now, however, at standard conditions, which is 25 degrees Celsius, H2O exists as a liquid. Therefore, option B is our answer and not option A, because at 25 degrees Celsius, H2O is not a gas. For question 9, Hess's law and Boyle energy data can be used to calculate the enthalpy change of a reaction. Bromoethane CH3CH2Br can be made by reacting ethane with hydrogen bromide. What is the enthalpy change for this reaction? Now, let's draw up the displayed formula for these molecules. So, plus HBr to produce CH3 CH2Br. Now, notice that the enthalpy change itself basically is summation of the energy released when bonds are formed and the energy that have been absorbed when bonds are broken. So now, let's look at the left-hand side, the reactant side. Now, for ethene, we need to break 1, 2, 3, and 4. 4 CH bonds. At the same time, we also need to break 1 CC double bond. We also need to break 1 HBr single bond. On the right hand side, we'll be forming 1, 2, 3, 4, 5. We will be forming 5 CH bonds. We'll be forming 1 CC single bond. We will be forming 1 CBr single bond. Now we need to refer to the data booklet to find their respective bond energy values. Now for this part, you need to be very careful because you don't want to suffer from parallax error and then write down the wrong values. This is not a tough question, but it can be quite tedious. So for HBr, the bond energy value is 366 kilojoules per mole, and we have one of them. For the CC double bond, 610. And for the CH bond, it's 410, but we have 4 of them, so 4 multiplied by 410. Add these values up. And the answer is 2,616 kilojoules per mole. Do the same thing for the peroxide. So 5 times 410. For CC single bond, it will be 350. Okay, let me just put this to this side here. Okay, so 350. And the CBr bond is 280. Add these values up. 5 times 410 plus 350 plus 280. 2,680. But this is must be given a positive sign because this is the amount of energy required to break those bonds in the reactants. Meanwhile, over here, this must be given a negative sign because this is the amount of energy released when those bonds are formed. So you sum these values up. That means positive 2,616 plus negative 2,680. And our answer shall be negative 64 kilojoules per mole. For information, this per mole is talking about per mole of the equations. So for this reaction, per mole of equation, it actually releases 64 kilojoules of energy. Let's look at the next question. Question 10. Which of the following is not a redox reaction? A redox comes from the two words reduction and oxidation. So that means we must be able to identify species that has been oxidized and another species that has been reduced so that it will give us a redox reaction. Now let's just look at option A. For option A, Mg plus 2HNO3, this is a metal plus acid reaction, which will give us our salt, magnesium nitrate plus the evolution of hydrogen gas. So the oxidation state of magnesium is 0 because anything in its elemental form, its oxidation state is always 0. Now, but for this case here, the magnesium has oxidation state of 2+. That means this has been oxidized. We are not going to look at nitrate because both sides have nitrate ions, but we're going to focus on the hydrogen. Because in this case, the hydrogen has a +1 charge, oxidation state of +1, whereas hydrogen gas is in its elemental form, so it has 0 oxidation state. So therefore, D hydrogen has been oxidized for this case here. Let me just have a look. This is +1 to 0, right? So this is 2 plus. Yeah, so this has been reduced. I got a bit confused. Yeah, this has been reduced. So therefore, option A is actually a redox reaction. Now let's look at option B. We have magnesium nitrate. Okay, actually there's no need to care too much about the coefficient. The coefficient will not decide whether it's a redox or not. Just need to write out the elements, the compounds, the products and reactants. That will be good enough. Notice I didn't put the coefficient in front because it's not crucial. Now, the magnesium has oxidation state of 2 plus. All right, oxygen has oxidation state of 2 minus. Okay, this one is 0, but we need to focus on this N actually. Okay, so let's just have a look at this first. Now, what's the oxidation state of nitrogen in nitrate? It's actually +5. But oxidation state of nitrogen in NO2 is actually +4, which means that the nitrogen itself has been reduced. Now we need to look for another one that has been oxidized, which is our oxygen, right? Because the oxygen has oxidation state of -2. But in this case, you notice the oxidation state of oxygen in O2 is 0. So this has been oxidized. Now, although this is -2, charge for oxygen here, -2, but because it has not been reduced, oxidized, from here to here. So we need to focus solely just on this O2, right? So therefore, you have both oxidation and reduction at the same time. So this is a redox reaction. Now let's look at the option C. SO2 plus NO2 to give you SO3 plus NO. Now the oxidation state of sulfur is +4 in SO2, but the oxidation state of sulfur in SO3 is +6. So therefore, sulfur has been oxidized. Now let's focus on the nitrogen. The oxidation state of nitrogen in this case is, because it's -2, this is +4. But the oxidation state of nitrogen in this case is -2. It's +2. So therefore, this has been reduced. Now probably you're asking, how do I know the individual oxidation states? Well, you need to know the group that those elements are in. So I give you a rule of thumb. If it's a group 1 element, then it typically has an oxidation state or charge of +1. Group 2 is +2, group 3 is +3, group 4 is +4 or -4, group 5 is +5 or -3, group 6 is +6 or -2, group 7 is +7 or -1. So in this case, since I'm trying to compare oxygen, I'll just let the oxidation state of oxygen be -2 because oxygen is a group 6 element. It either forms +6 or -2. But it's easier for it to gain 2 electrons compared to losing 6 to achieve the noble gas configuration because 2 is lesser than 6. So as you can see, both A, B, C are redox reactions. But let's try to satisfy our curiosity why option D is not a redox reaction. Now, SO3, sulfur trioxide plus H2O to give us our sulfuric acid. The oxidation state of sulfur in SO3 is +6. This is also +6. Hydrogen +1, +1, -2, -2. Right, so none of the elements has been oxidized or reduced. Therefore, this is not a redox reaction. Let's look at question 11. The reaction between sulfur dioxide and oxygen is reversible, and we are given enthalpy value. So this question requires the knowledge of Le Chatelet's principles. So let me just write the equation down first. 2SO2 plus O2 to give you 2SO3. And this enthalpy change is exothermic. We do not need to know its absolute value. We just need to know whether this forward reaction itself is exo or endo. So it's exothermic. Now, pressure will only affect gaseous particles. So sulfur dioxide is a gas, oxygen is a gas, and sulfur trioxide is also a gas. Therefore, if you apply different pressure levels, the partial equilibrium will shift accordingly. So now, which conditions of pressure and temperature favor the reversed reaction? So that means we want the reaction to proceed backward. So now that you know that this is a gaseous system, and you want the partial equilibrium, in short POE, to shift towards the side with more moles of gas, because 2 plus 1 is 3 moles, but here you have 2 moles. That means you must apply a low pressure, because when there is a low pressure, or by raising the low pressure means you actually raise the volume, right? Because pressure is inversely proportional to volume. Okay, so if you want to have low pressure, that means you raise the volume. So that means when there is a low pressure, based on Le Chatelet's principle, the positional equilibrium will shift towards the side with higher pressure, which means more moles of gaseous particles. Hence, options C and D should be considered and not A and B. Next, this forward reaction is an exothermic one. So how I teach students is that you just take it that if the product is favored, this side will be rather hot. Let me use a different pen. This side will be rather hot because heat is released. So this side will be rather cold. So if you raise the temperature of the system, the partial equilibrium will shift towards the colder end. Hence, the answer for question 11 is option C. Now for question 12, which statement about the effects of a catalyst on a reversible reaction is correct? Let's go through all the options. The activation energy of the forward reaction stays the same. That's not true, because let's do draw a very simple energy profile diagram. Assuming it's exothermic reaction. Now this is your energy level, and this is your progress of reaction. Okay, so now if you introduce a catalyst, there will be a catalyzed reaction with a lower activation energy, because previously activation energy is so high, but now it's lowered, right? Because the catalyst is a substance that provides an alternative pathway with a lower activation energy. That means both your forward activation energy and your backward activation energy are actually being reduced. So you can't say that the activation energy stays the same. Now, for option B, the composition of the equilibrium mixture stays the same. Now, in this case, this is absolutely correct, because the position of equilibrium will not be affected by the presence of catalysts. Now, for information, in this case, this big K is our equilibrium constant. The equilibrium constant is actually a ratio of the forward rate constant. This is a forward rate constant, all right? I put in a small k over the backward rate constant. And the rate constant itself, maybe I just put a prime to denote that I'm referring to the rate constant. So the rate constant itself is actually dependent on the activation energy as well as the temperature. Right, this is actually known as our Arrhenius equation. Right, I'm going to spell it out. Arrhenius equation. So this A is actually a pre-exponential constant, just a constant. EA is an activation energy, R is a molar gas constant, and T is our temperature. So as you can see that the rate constant is only dependent by the presence of catalyst, because it will affect the activation energy and the temperature. And the equilibrium constant is a ratio of the forward rate constant over the backward rate constant. So if you raise the temperature, or in this case you change the temperature, or you use a catalyst, right? So if let's say the rate constant increases, like in this case here, if you use a catalyst, the rate constant will increase, but they will increase by the same proportion. For example, if the flow rate constant increases by 2 times, the barrel rate constant also increase by 2 times, which means that they'll cancel off each other, keeping the equivalent constant the same. In short, equivalent constant is only affected by temperature. So, option B is our correct answer. Now, option C, the rate of the backward reaction stays the same. As I mentioned earlier, when you introduce a catalyst, both your forward rate and the backward rate will increase by the same extent. So C is not correct. The value of the equivalent constant changes, that's also not correct, because the equivalent constant is a ratio of the forward rate constant over the backward rate constant. Now, let's look at question 13. Which oxide is insoluble in aqueous sodium hydroxide? The word insoluble or soluble actually just means that can it react or not? In other words, I can actually replace this question as which oxide cannot react with aqueous sodium hydroxide? Now, MgO itself is a basic oxide. So MgO itself is a basic oxide because it's a metal oxide. So react with acid. A base reacts with acid. Right. So, but sodium hydroxide is a base. So therefore, there's no reaction with another base. Aluminum oxide is an amphoteric oxide. Amphoteric, the word amphoteric sounds very similar as amphibian. A frog is an amphibian. That means you can live both on land and in water. So amphoteric oxide means it can react both acid and a base. So therefore, although it's a metal oxide, right, it's a basic oxide, however, it's amphoteric. So it can actually react with sodium hydroxide as well. P4O10 is a non-metal oxide, so it is an acidic oxide. And acidic oxide will react with a base. SO2, sulfur dioxide. This is an acidic oxide because it's a non-metal oxide. So therefore, it's acid oxide means it will react with a base. Hence, the answer is option A. Magnesium oxide will not react or dissolve in aqueous sodium hydroxide. Next, X, Y, Z are three elements in the third period. X reacts with chlorine to give a liquid product. Y reacts with chlorine to give a solid product that dissolves in water to give a solution of pH 7. Z reacts with chlorine to give a solid product that dissolves in water to give a solution of pH 6. Now, let me just write down all the elements for the period 3 so that it's easier for us to compare and contrast. Sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon. Now, argon is a noble gas, so it won't react. It's a noble gas, so it won't react. So we are not going to consider this. Now, one thing to note, the giveaway clue is actually the second statement. Y reacts with chlorine to give a product that dissolves in water to give a pH 7. Now, NaCl, MgCl2, AlCl3, SiCl4. The phosphorus will give you things like H3PO4, H3PO3. Okay? Now, S will give you things like SCl2, etc. Now, sodium chloride is our table salt. So due to the low charge density of sodium ion, therefore, its pH is 7, which actually tells me that Y is sodium. Y is actually sodium. Next, Z actually is our magnesium, because Mg2 plus has a rather has a high charge density, not that high as compared to Al3 plus, because AlCl3 actually gives you a pH of around 3 when dissolved in water. But still, it can polarize electron cloud the oxygen, for instance, right? So it can actually get deprotonated, so to speak, because due to high charge density. So it gives you around pH 6 to 6.5. Right? All these are actually in our content syllabus. So if you know that, that means Z itself will have to be magnesium. Bear in mind that sodium chloride is an ionic compound, so it's a solid at room temperature and pressure. Magnesium chloride is also an ionic compound, so it's also a solid. But from AlCl3 onward, all these are liquid and solid and gases because they are simple molecules. In fact, AlCl3, aluminum trichloride, has a boiling point of 180 degrees Celsius. So therefore, it's a liquid, right? So hence, although we can't identify what X is, we just know that X could be either aluminium, silicon, aluminum, silicon, phosphorus, sulfur, chlorine, etc. But we know that in terms of they are non-metals. So all these so-called, okay, over here, are they good conductors of electricity? Well, we know that aluminium is a good conductor of electricity. The problem is that we are not sure, we are not given enough information that X is Al, because X could be silicon, it could be phosphorus, sulfur. We are not given enough information. But what we can tell for sure is that Y and Z is sodium and magnesium respectively, and they are good conductors of electricity. Electrical conductivity is actually dependent on the availability, okay, of a mobile charge carrier. That means firstly you must have charge carrier in terms of electrons or ions, and they must be mobile. So Y and Z are metals, therefore they can conduct electricity. Hence, answer is option B. Now for question 15, a solution contains both Mg2+ and strontium2+ ions at the same concentration. The solution is divided into two equal portions. Aqueous sodium hydroxide is added dropwise to one portion. Dilute sulfuric acid is added dropwise to the other portion. Which row is correct? Now to solve this question, we need to know our group 2 chemistry. In other words, we need to know the solubility. So for information, for this case here, group 2 hydroxide, the solubility increases down the group. Group 2 carbonates and sulfates, their solubility decreases down the group. The reason for that can be explained using this equation. Delta H solution equals delta H hydration minus lattice energy. Now, so in this case here, which precipitate will be seen first? Now, if you understand that the group 2 hydroxide solubility actually increases down the group, so therefore, let's check. Strontium hydroxide versus magnesium hydroxide, which is actually more soluble? Well, strontium is below magnesium in the group 2. So strontium is actually more soluble compared to magnesium hydroxide, which means that we should see the PPT of magnesium hydroxide first. Hence, you have to rule out the option C and D and only consider the options A and B. Next, let's look at the sulfate portion. So we add sulfuric acid. Which PPT will be seen first? Now, using the same argument, strontium sulfate versus magnesium sulfate, which is less soluble? Strontium sulfate is less soluble because the solubility of sulfate and carbonate will decrease down the group, which means you're going to see this PPT first. Therefore, strontium sulfate will be the PPT first seen. Let's look at, this is for question 15. Let's look at our question 16. For question 16, the volatility of the group 17 elements, or sometimes called group 7 elements, chlorine, bromine, and iodine decreases down the group. What is responsible for this? If something is more volatile, it means that it has a lower boiling point. That's why it's more volatile. So since the question is telling us that the volatility actually decreases down the group, that means the boiling point actually increases down the group for group 17 or group 7 elements. To know the reason, we have to identify the structure that these halogens possess. These are simple molecules. They adopt simple molecular structure. So for simple molecular structure, we are going to look at their IDID, which stands for instantaneous dipole-induced dipole, which is proportional to the number of electrons per molecule, or sometimes people say the MR, molecular mass size. In fact, saying that it's dependent on MR is not really true. It's actually dependent on the electrons. However, we know that if the species has more electrons, it must have a greater MR. So therefore, this explains why we usually say that IDID is actually proportional to MR. So if you understood that, then the answer is obvious. It will just be option D, because more electrons means you have a larger electron cloud size, which means that the electron clouds is more easily polarized. So you are able to form this delta plus, delta minus, greater delta plus in terms of magnitude, delta plus and delta minus. For question 17, bromine is extracted from the seawater. In the final stages of the process, two redox reactions takes place. Which row is correct? Now actually for this question, we can actually rule out a few options. If you know that Cl2 is a more powerful oxidizing agent than Br2, then you just need to look for the options that does not have Cl2 placed on the left. So A is obviously wrong, because Br2, bromine, is a weaker oxidizing agent than chlorine. We can also rule out option D, because option D has Br2 on the left of chlorine. So this leaves us with just option B and C. So now, an oxidizing agent itself wants to be reduced. A reducing agent itself wants to be oxidized. So if you look at the oxidation state, let me write out the equation first. Now, the oxidation state of bromine in Br2 is 0, but over here is -1. So bromine has been reduced, which means that in this case, bromine is serving as an oxidizing agent relative to the other species which you want to compare, which is SO2. That means Br2 is a stronger oxidizing agent than SO2. Hence, the answer is obvious, it's just B. In fact, if you know your redox chemistry, you know that sulfur dioxide is a very famous reducing agent. And to test for sulfur dioxide, which is a reducing agent, we need to use an oxidizing agent, which could be either potassium permanganate, the purple solution, or the orange dichromate. But to satisfy your curiosity a little bit more, let's look at the other equation, 2HBr plus Cl2 to give you Br2 plus 2HCl. As I mentioned, the coefficient is not important. It's the identity of species that are more important. So now you see over here, in this case, a chlorine has oxidation state of 0 to a -1, which means it wants to get reduced, which means that it is an oxidizing agent when confronted with Br-. Okay, so over here, this is the most powerful oxidizing agent out of those three species. Let's look at the next question. Question 18. When burnt, sulfur forms a gaseous product X, which can be oxidized to produce a gas SO, that gas will be SO3 actually. So let's see. So sulfur burns in oxygen to form your sulfur dioxide. This is X, which can be further oxidized to give you SO3. This is Y. How do you know it has been oxidized? Because there's an increase in the number of oxygen atoms from 2 to 3. And the gas Y, which is SO3, will react with water, balance your equations. What we have is H2, SO4. So this is our Z, our acidic solution. Now once you are able to identify the identity of X, Y, and Z, then we can start to determine their respective oxidation state. The oxidation state of sulfur in SO2 is +4. The oxidation state of sulfur in SO3 is +6. And oxidation state of sulfur in sulfuric acid is +6. So it's +4, +6, and +6. Therefore, answer is option D. For question 19, one molecule of ammonia reacts with one molecule of ethyl methanoate to produce one molecule of methyl and only one other molecules. Now, which is X? Let's see what X is. First, let's draw our ethyl methanoate. Plus our ammonia. So what happens is that the product form is HCO and H2. That was what the question to us. So therefore, this portion has been removed. And you also lost a H as well. Therefore, X has to be ethanol because you have a H plus O, C2, H5. This is our ethanol molecule. Next, so for Y, we have one methylamide decomposes on strong heating to produce one molecule of ammonia. Now, this species gives you one molecule of ammonia. So ammonia means what? You have this and this. And what are you left with? You are just left with a CO. So therefore, you are left with a carbon monoxide. Actually, there's a way to represent why this reaction occurs via electron arrow pushing. But I'm not going to go into that because it's a bit more complicated. Now, let's look at question 20. What type of stereoisomerism are shown by 2,4-dimethyl hex-2-ene? Now, I encourage students to learn how to draw the skeletal formula. So, because it's a lot quicker. Hexane, right? The parent chain is hexene. So, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So, you have 6 carbon atoms. Hex-2-ene means the double bond occurs between the second and the third carbon. So you can just do a numbering of the atoms. 1, 2, 3, 4, 5, 6. So therefore, the double bond occurs between carbon 2 and carbon 3. Hence, it's called Hex-2-ene. Next, we need to put in the substituent. We have 2 substituents. They are the methyl substituent. 2-methyl. So this is CH3. And 4-methyl at the 4th position. Now, let's check. Does this molecule exhibit cis trans? Well, if you want to check whether it's cis trans, the first criteria is that there must be a double bond, in this case here. Right. Of course, this is not the only criteria because certain molecules like cycloalkane can also have cis trans. But I'm saying that the generic way of saying is it will have an alkene, CC double bond. So this does not exhibit cis trans because the carbon that is connected, or rather the substituent that is connected to this carbon atom, both of them are the same. So this molecule does not exhibit cis trans. However, it does have a chiral center. Where's the chiral center? At the carbon 4. Because it has 1, 2, 3 and an invisible H. 4 different substituents connected to this carbon. So this carbon is chiral and it does not have any internal plane of symmetry. Therefore, it can only exhibit optical isomerism. Let's look at question 21. An organic ion containing a carbon atom with a negative charge is called a carb anion. An organic ion containing a carbon atom with a positive charge is called a carbocation. The reaction between aqueous sodium hydroxide and 1-bromobutane proceeds by an SN2 mechanism. Because your bromobutane itself, if you draw it out, 1, 2, 3, 4, methane broken. Sorry about that. So butane means it has 3 carbon atoms. So 1, 2, 3, and then there's a Br. All right, because methane, ethane, propane, butane. Sorry about that. 4 carbons. Methane, ethane, propane, butane. Yeah, 4 carbons, and there's a Br. So let me number carbon atoms. 1, 2, 3, 4. So this is a primary substrate, primary RX, primary alkyl halides. So there's less steric hindrance, hence it can be susceptible to an incoming nucleophile and proceeds via SN2 mechanism. So this carbon 1 will be given a delta plus charge. This bromine will be given a delta negative charge because bromine is more electronegative than the carbon atom. Hence, your hydroxide ion, the nucleophile, the lone pair from the oxygen atom will attack this carbon atom and cause a simultaneous forming of the CO bond and the breaking of the CBr bond to form a pentavalent complex, which cannot be isolated, by the way. Now that you know its mechanism, therefore the answer in this case will be obvious, which is option A, because the first step involves the attack by a nucleophile on a carbon atom with a partial positive charge. So let's look at questions 22. Compound X can be converted into compound Y in a single step. So what I usually do tell my students is that you always count the number of carbon atoms. So as you can see in this case here, your product Y, compound Y, actually has 1, 2, 3, 4, 5, 6, 7, right? 1, 2, 3, 4, 5, 6, 7 carbon atoms. Let's check the number of carbon atoms for A as well. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Now, in that case, my favorite option will be A and B. However, let's just double check. Because you have an alkene, right? All these 4 options give you an alkene, and in the end, they give you a carbonyl, which is a ketone, in this case, a carboxylic acid. Now, ask yourself this question. What are the reactions involved for alkene? Well, an alkene can undergo electrophilic addition. An alkene can undergo oxidation. You can actually divide them into mild oxidation, which forms a diol, and strong oxidations as well, which leads to oxidative cleavage. Now notice that A, B, C, D are all cycloalkene, cyclic compounds, and suddenly your compound Y is an aliphatic compound, a single chain compound, which suggests that there is oxidative cleavage. Now, you just need to do oxidative cleavage for A, B, C, and D. You'll notice that the only option in this case is option A. So let me just look at the option A first. Right, I'll just consider option A. You can work out B, C, D by yourself. So you're going to do an oxidative cleavage. Don't forget there's an invisible H here. So I'm going to name the carbon atoms so that to avoid confusion. 1, 2, 3, 4. Maybe I'll put a 5 here, and put a 6 here, and I'll put a 7. So once you have oxidative cleavage, the reagents used is either hot acidified KMnO4 or hot alkaline KMnO4. However, because in this case Y is a carboxylic acid, the reagents and conditions used will be hot acidified KMnO4. It is a temperature that decides whether alkene undergoes strong oxidation or mild oxidation, not the medium. So what we have is 1, 2, 3, 4, 5. So let me just do it this way first, okay? Okay, it's not drawn very nicely, but it's okay. So I just put yeah, oops, there's a C here. So let me just put a number again. 1, 2, 3, 4, 5, 6, and 7. This is a methyl group. Now, because it's aldehyde, and aldehyde can be further oxidized to give a carboxylic acid. Then you notice that the answer is just option A. Now let's look at question 23. Which compound reacts with 2,4-dinitrophenylhydrazine reagent but does not react with Tollens reagent? 2,4-dinitrophenylhydrazine is a test for carbonyl compounds, but it does not react with Tollens reagent. A Tollens reagent tests for aldehydes, both aliphatic and aromatic aldehydes. That means the compound that we are interested in must be a ketone, because a carbonyl comprises either ketone or aldehyde. Since we want something that cannot react Tollens, that means we do not want aldehyde. All we want is ketone. So option A has a ketone. Right? Learn to recognize the structures, the homogeneous group, based on the chemical formula. CH3CO, so there's a CO here, that means this is a ketone. Over here, when you see CHO, this is an aldehyde. So option B is out. Option C, you have a ketone, because of CO, and CHO, which is aldehyde. Option C is also out. Option D contains a hydroxyl group, which means this is an alcohol. And alcohol cannot react with 2,4-dinitrophenylhydrazine. Sometimes it's also known as the Brady's reagent. Brady's reagent. B-R-A-D-Y apostrophe S reagent. Hence, the answer is option A. Let's look at question 24. Structural isomerism and stereoisomerism should be considered when answering this question. The molecular formula of compound X is C5H12O. If you know your degree of unsaturation, the calculation, you notice that its degree of unsaturation is 0, which means that everything is all saturated, everything is all single bond. So it reacts with alkaline aqueous iodine. This is a haloform test, or sometimes people call it triiodomethane test, because it will generate a yellow PPT, which is CHI3. So now, since to form a PPT with a triiodomethane test, you must either have this moiety, which is a methyl ketone, or this particular moiety, which contains a hydroxyl group. Since the degree of unsaturation for C5H12 is C5H12 oxygen is 0, we have to rule this option out, because this has a degree of unsaturation of 1. Therefore, we should only consider anything with the hydroxyl. And it must possess this particular part, OHHCH3. So now let's look at the options available. This is out because the OH does not satisfy this criteria. Option B is also out because you have OHCH2 and CH3, not OHCH3. So you can only consider option C and D because there's OHCH3, OHCH3, and there's H here. But now here's the thing. Why do we accept option C and not option D? Now let's draw the structure of C and D to have a closer look. So we have for option C, what we have is CH3, CH3, C, H, OH, and a CH3. So we do have this group here. But we're going to do a dehydration. So I'm going to draw this a little bit differently so that I can see a little bit better. I'm going to draw a display formula. So over here, when you perform dehydration, you can remove OH and H over here, or OH and H over here. Now try to visualize by yourself. Because if let's say you remove the OH and H over here, what you have is an alkene, and it's a terminal alkene, because there's a double bond here and the CH. And there's no cis trans involved because you have two H on the same carbon atom. Now if you remove the OH and the H over here, what you have is there's another alkene here, but there's no cis trans because this carbon will have two CH3. The same two substituents are on the same substituents identity are on the same carbon atoms, so there's no cis trans. Therefore, the only isomers that you have is 2. Right? So try to visualize in your mind without really drawing everything out, because time is precious. But if you look at option D, let's draw this out first. I'm going to draw a display formula, so it's probably easier for the audience to visualize. So now you can either remove the OH from here, either one of these 3 H's, and you're going to form this double bond here. Alright, so there's no cis trans here, so that's one molecule for you, one alkene for you. The other way is this one, OH and another H. Then I put a double bond here. But now you notice that actually you can have cis trans, for this case here. You can have a cis trans because this is one substituent. Oops, sorry. Right, so in this case, you can either remove here when there's no cis trans, or remove from here when there's cis trans. Can you see the cis trans? If you remove here, you put a double bond here, you notice that this carbon has two different substituents, a H and a ethyl group, a H and this whole group itself, H and a CH3. So therefore, you have cis trans over here, so you have two alkenes, two possible alkenes, and one alkene here. So this one is going to give us 3 different alkenes instead of 2 alkenes only. Hence, the answer can only be option C. Let's look at question 25. Which volume of hydrogen measured under room conditions is produced when 0.160 grams of methanol reacts with an excess of sodium? So now let's write our equation first. CH3OH, this is an alcohol, and alcohol can react sodium. This is known as a redox reaction. Some people call it reduction of alcohol, but there's evolution of hydrogen gas. So 1 mole of alcohol will produce half a mole of hydrogen gas. So first we need to determine the number of moles of CH3OH, our methanol, by using a formula mass over MR. So 12 plus 3 plus 16 plus 1. So the MR for this case here for methanol is 32. So the number of moles will be 0.16 divided by 32, which is 0.005. Because the mole ratio of alcohol to hydrogen is 1:2. Okay, so in other words, over here we must divide by 2. So the number of moles of hydrogen will be 0.0025 moles. 0.0025 moles. Because what we have is, in this case here, 1:half. So the number of moles of hydrogen involved is 0.0025. Since it's under room conditions, so the molar volume at room conditions is 24 dm cubed. So we multiply by 24 dm cubed. So 0.0025 multiplied by 24, and what we have is 0.06 dm cubed. Convert to cm cubed, and it will be 60 cm cubed. Hence, answer is option A. Let's look at question 26. Which volume compound X produces a carboxylic acid when heated under reflux with acidified potassium dichromate, which is orange in color. Compound X does not react with sodium metal. What could be identity of compound X? Now, in this case here, let's go through all the options. Option A, propanol. It can produce a carboxylic acid because it's an aldehyde. B, propanone. You look at the last three letters, the suffix ONE, so it's a ketone. A ketone cannot be further oxidized, so B is out. D is also out because propan2-ol tells us that this is a secondary alcohol. A secondary alcohol can only be oxidized to a ketone. So the answer could only be either A or C, because propan1-ol will get oxidized to an aldehyde, which is propanol, which can be further oxidized to a carboxylic acid. However, the next statement tells us that compound X does not react with sodium metals. Our alcohol can react with sodium metal, as you saw in question 25. This is a redox reaction. Propanol cannot. So I just draw out how a propanol looks like. Propanol also have 3 carbons, methane, ethane, propane, so 3 carbons. Alright, it must have a C double bond OH, a moiety, 3 carbons, so you can just put CH2, CH3. Whereas for our propanol, okay, I'm using a skeleton for this case. CH3, CH2, CH3, OH. So this one can react with sodium metal to give you, okay, let me just draw over here, to give you our O minus Na plus half H2. Okay, let's look at question 27. A reaction occurs when a sample of 1-chloropropane is heated under reflux with sodium hydroxide dissolved in ethanol. So, what is our reaction? Well, 1-chloropropane is RX, is an alkyl halide, RX. Okay, alkyl halide, so in short, called RX. Now, if you react with sodium hydroxide in alcoholic medium, you are going to get an alkene. However, if you react RX with sodium hydroxide in aqueous medium, you are going to get an alcohol. Now, it doesn't mean that there's no alkene involved. It's just that alkene will be a minor product. Whereas in this case, this will be major. In this case, alkene will be major plus ROH. Alright? Definitely both products will be formed. It's just that which is the major, which is the minor product. So since we are using sodium hydroxide dissolved in ethanol, this is an alcoholic medium. So this will be an elimination reaction. So it's either A or B. And if it's an elimination reaction, we will get an alkene. And propane is an alkene because if you look at the last 3 letters, the suffix -ene, E-N-E is an alkene. So question 27's answer is option B. For question 28, ethane diacid has the formula so and so. Now, how does ethane diacid looks like? It looks like this. You have 2 carboxylic acid groups. Okay, and of course, what's the charge that they have? Well, if you deprotonate this species, this will be -1, -1. Hence, if deprotonate this dicarboxylic acid, what we have is C2O4 2-. It has an oxidation state of 2- because 2 protons could potentially be lost. And we know that aluminium ion has a charge of +3. Hence, the answer can only be option D. For question 29, alcohols, aldehydes, and nitriles can each be converted into carboxylic acids. Which descriptions of their conversion into carboxylic acids are correct? Well, alcohol can be oxidized to become a carboxylic acid. Same goes for aldehyde. So answer can only be option C and D. For nitrile, how does a nitrile looks like? R, C, triple bond N. The R is an alkyl group. Alright, there are only two reactions they can undergo. One of them is reduction process via lithium aluminum hydride and gives us our primary amine. You just add your 4 capital H when you balance the equation. RCH2 NH2. Or it can be hydrolyzed. If it's acidic hydrolyzed, what we have is carboxylic acid. If it's alkaline hydrolyzed, we will get a carboxylic ion. So these two are your hydrolysis process. Hence, the answer for question 29 is option C. Now for question 30, we need to know a little bit about IR, infrared spectroscopy. How many structural isomers with the molecular formula C4H10O give IR absorptions both at approximately 1002 per cm and approximately 3004 per cm? Now first you need to find the degree of unsaturation for C4H10O, which is 0. That means everything is all single bond. And because it's O, you see, there's an oxygen atom and there's only one. The first thing that comes to your mind is that it's probably alcohol. Now, but we need to verify whether it's indeed alcohol. So if you refer to our data booklet, under the page on IR, what you have here is the following. You may not be able to see clearly, but, well, there's an O, CO, can either be alcohol, ether. Ester is not possible because ester has 2 oxygen atoms. Carboxylic acid is also not possible because it has 2 oxygen atoms. So it could either only be alcohol or ether. We are looking for 1002 per cm, so both species fit the bills. Now, however, we look at the 3004. That means the OH. Okay? Because if let's say ether itself, ether actually has CO bonds. So the CO bonds itself has no 3004. But when you see 3004, always remember, when you see 3004 per cm, the first thing that comes to your mind has to be hydrogen bonding. Hydrogen bonding, okay? So therefore, you have ROH, okay? Alcohol, yeah, 3004 because it's from 3002 to 3006. Hence, this must be alcohol. Once you know that this is an alcohol, we can start to draw our isomers. I advise you to use your skeleton formula to draw isomer. So because there are 4 carbons, so let's start with the parent chain with 4 carbons. 1, 2, 3, 4. Okay. But now we need to put our our OH. Alright, so I just leave this backbone here first. So 1, 2, 3, 4. So you can either put an OH over here. 1, 2, 3, 4. You can put an OH over here. Alright. You are not going to put another OH over here, see, because, okay, let me show you what I mean. 1, 2, 3, 4. You are not going to put the OH here. Because these two are the same. Right, same goes for if you put the OH at this carbon atom, it's going to be the same as this one. So therefore, for n equals to 4, you have 2 potential isomers. Now we need to move to n equals to 3. Okay, so n equals to 3. Right, 1, 2, 3, but because it's 4 carbon, so it's over here. Right, so this will be your backbone. 1, 2, 3. Now we put our OH at this spot. Putting at this spot is the same because they're equivalent. These 3 methyl groups are equivalent. Or 1, 2, 3. Like this time around, you put the OH at this spot. So you notice that over here you have 2 potential isomers as well. Okay. Is it possible to go further down if n equals to 2? Well, it's not possible because you never add the substituent to the terminal carbon because you will just go back to the previous one. Okay, so the lowest n you can go is only 3. Therefore, 2 plus 2 gives us 4. Hence, the answer for question 30 is B. Now let's look at question 31. Now, question 31. Compound Q contains 40% carbon by mass. So now to solve this question, you actually have to find out the whole MR of carbon atoms. In this case, you have 12 times 6, right? Because the AR of carbon is 12, you have 6 of them, 12 times 6. Over the entire MR of glucose, which is 12 times 6, plus 1 times 12, plus 16 times 6. I hope you know how I got these values, because you have 6 carbon atoms and AR of carbon is 12. You have 12 hydrogen atoms, AR of hydrogen is 1. And you have 6 oxygen atoms and AR of oxygen is 16. So you will do a calculation, multiply them by 100%. So let's just do the calculations first. Twelve times 6 divided by 180. So indeed, this is 0.4 or 40%. Apply the same technique for starch. Okay, but you see, there's n over there. It doesn't really matter. It just tells you that there are many of them. So all we need to do is just same thing. 12 times 6 because there's 6 of them. But now divide by the m of starch, which is 12 times 6 plus 1 times 10 plus 16 times 5. Right, because you have 5 oxygen atoms and 10 hydrogen atoms. Then let's work it out. (162), so what we have is 0.444. 0.444. So that's not what we want. So option 2 is already out. Now if you look at the options given, you notice that if option 2 is ruled out, the answer can only be D. Right? So I'm not going to do the one for sucrose. You can try out by yourself, but it's the same technique. 12 times 6 over the entire MR of sucrose. And then you see for yourself whether the compound sucrose contains 40% carbon by mass. Question 32. Now, a container is partially filled with hot water, sealed and left to cool. Which statements are correct? Well, statement 1, as the temperature decreases, water molecules lose kinetic energy. That's correct. That's what we learned in the kinetic particle theory during our secondary school days. So, because higher temperature means the molecules have more kinetic energy to move about. So 1 is correct. As the temperature decreases, more water molecules move from vapor to liquid. That's true because now the temperature has dropped. So the molecules have less kinetic energy available. So they can't really overcome the intermolecular forces that easily. So statement 2 is correct. Statement 3, as temperature decreases, the vapor pressure of water decreases. Now, this is like a continuation from option 2. Because when temperature decreases, now more molecules move from vapor to liquid. You need to understand that the vapor pressure of solid will always be less. I'm putting double two arrows over here to show it's really a lot lesser than the vapor pressure of a liquid, than a vapor pressure of the gas. Because the gas is already a gas, so of course its vapor pressure will be there. It's the pressure exerted by the vapor. So option 3 is also correct. Question 33. Ammonia and chlorine react together in the gas phase. Which statements are correct? Ammonia behaves as a reducing agent. Well, a reducing agent itself gets oxidized. Did it get oxidized? Although I mentioned there's actually no need to put the coefficient there in this case, right? But I just put it for completion's sake. Now, the oxidation state of nitrogen in NH3 is -3. The oxidation state of nitrogen in N2 is 0. Therefore, it has been reduced. If it has been reduced, that means it's serving as a, it has been oxidized, sorry. It has been oxidized. If it has been oxidized, that means it's serving as a reducing agent. So option 1 is correct. Okay. Now, then for option 2, it behaves as a base. That's true because in this case, it's more like a Bronsted-Lowry base. A Bronsted-Lowry base will gain a proton. Well, your NH3 has gained a proton to form your NH4+. So it is a base. Last option, the oxidation number of hydrogen changes. Well, the oxidation state of hydrogen in NH3 is +1. Over here is still +1, so there's no change. The oxidation state of chlorine over here is -1. Over here is -3 for nitrogen, -3. So answer for 33 is option 1 and 2. 34. In which reaction does NH3 behave as a Bronsted-Lowry acid? By definition, a Bronsted-Lowry acid is a proton donor. So for option 1, NH3 is actually serving both as a proton donor and a proton acceptor, because when NH3 loses a proton to form NH2-, this is actually what we call an amide, A-M-I-D-E. It's not the amide that we see in organic chemistry, right? This is amide in inorganic. This is called an amide ion. So this has lost a proton to form and as an acid, but over here NH3 to form NH4+, it has gained a proton. So it's behaving as a Bronsted-Lowry base. But in this case, it's taking on the role of two identities. For option 2, H, SO4- and NH3. So the NH3 lose a proton? No, it gains a proton. So that means NH3 is behaving as a Bronsted-Lowry base and not an acid. Over here, NH3 is serving as a ligand. This is something that you learn in the transition metal chapter. This is a complex ion. In fact, this is the product is actually our diamine silver or Tollens reagent. So answer is just option 1. For question 35, now we need to know the equations when chlorine reacts with hot aqueous sodium hydroxide. Okay, I'm not balancing equation, I just write the species forms and react for 35. Right, so your chlorine gas plus NaOH, this under hot conditions, okay, hot conditions, is going to give you your NaCl plus NaClO3 plus your H2O. Okay, this under hot conditions. So the oxidation state of chlorine over here is 0 in Cl2. Over here is -1. Over here is +5. So that means chlorine has been simultaneously oxidized and reduced. It has been reduced, it has been oxidized. So this is actually known as a disproportionation reaction. So do we have any -1 here? Yes, we do. Do we have any +5 here? No, we don't. Right. However, if let's say this is done in cold conditions, cold, then what we have is actually NaCl plus NaClO, not O3, plus H2O. So it's -1 and +1. Okay, so hence the answer for this question is just option 1. For question 36, in which different forms does nitrogen exist in compounds? Well, it can be bonded by triple bonds such as nitrogen gas. As part of a cation, yes, we have ammonium ion, NH4+. In an oxidation state of +5, now this is not something that's easy to visualize, to think on the immediately actually. But if you know that nitrogen is a group 5 or group 15 element, it will typically have oxidation state of +5 or -3. So plus 5 is definitely possible. So I give you an example, and that will be NO2 plus, our nitronium ion. An electrophile that is used in electrophilic substitution of benzene ring. How does NO2 plus look like? It's a linear molecule. A hybridization state, if you recall, is sp hybridized 180 degree for the bond angles. So oxygen, group 6, -2, so -4, so this will be +5 oxidation state for nitrogen. So for question 36, all the options are correct. For 37, polyethylene and PVC are examples of addition polymers. Now for information, PVC stands for poly means you're going to have polymerization, vinyl chloride. That's why you have PVC. Okay, how does it look like? Well, its monomer looks something like this. It's an alkane, but there's a Cl. So vinyl chloride. So it can undergo addition polymerization. Now that we know how a PVC looks like, of course we also know how ethene looks like. On combustion, PVC can produce carbon monoxide because of incomplete combustion. Complete combustion will give you CO2 and HCl because there's a chlorine over here. So option 1 is correct. When polyethylene is burnt in a landfill site, it will not significantly biodegrade. That's correct because you can visualize polyethylene as a plastic. Plastic is non-biodegradable. For option 3, the empirical formula of an addition polymer is the same as that of the monomer. That's true because if you want to represent this as polymer, what people usually do is they just convert this CC double bond into a CC single bond, straighten this up, and just put a N there to represent that this is a polymer. Right? This is actually what we call a repeating unit for this addition polymerization. So all the 3 options are correct for question 37. For question 38, the organic compound X gives a precipitate when warmed with aqueous silver nitrate. Now, silver nitrate itself cannot be used directly to react with this compound. As you see, this is actually an RX compound, alkyl halide. You need to add in sodium hydroxide heating. Now after that, you need to acidify, cool it before adding silver nitrate. Right, but I'm not going into those details. But we know that under QA, qualitative analysis, silver nitrate is a test for halides. So compound X must be an alkyl halide, so that it can get PPT such as AgCl, silver chloride, silver bromide, silver iodide, etc. And the PPT dissolves when concentrated aqueous ammonia is added. What could X be? If you subject 1 bromopropane to those tests, silver nitrate, you're going to get silver bromide. You're going to get silver bromide. Silver bromide can dissolve in excess aqueous ammonia. So to form this. This is our complex ion. Okay, the complex ion is soluble because it can form ion dipole with water, but it requires a concentrated ammonia solution. Whereas for silver chloride, that means because 2-chlorobutane can give us chloride ion, so we get silver chloride when reacted with silver nitrate, plus 2NH3, same reaction. Okay, same way of writing this equation. We are going to form a complex ion, the diamine silver. But in this case, chloride ion is generated. But this one requires concentrated. This one, for AgCl, aqueous is sufficient. If you want to use concentrated, it's even better. But for option 3, AgI cannot react with your NH3, not at all. So what does this example actually tell us? It actually tells us that the KSP, the solubility product, of AgCl is greater than that of AgBr is greater than that of AgI. Okay, this is the information that we can derive. For question 39, propanol reacts with hydrogen cyanide to form 2-hydroxyl butanediol. Sometimes we call it halohydrine. A suitable catalyst for reaction is sodium cyanide. So if you see NaCN on top of the arrow, it usually says that this is probably a catalyst. Now, HCN is a weaker nucleophile than the nucleophile provided by NaCN. This is true. That's because HCN is a weak acid. That means if it's a weak acid, it's not going to generate sufficient your cyanide nucleophile. All right, so I'm going to write it down. 39, because HCN is a weak acid, so I'm going to give you H plus Cn minus. Because this is a weak acid, so we are going to use a reversible arrow. Hence, the concentration, that means the amount of cyanide ion generated from HCN will be lower compared to, say, NaCN. Because NaCN also sodium salts are soluble, so it's going to give you a lot more cyanide ion. Imagine you use 1 mole of HCN, it will give you less than 1 mole of cyanide ion. But if you use 1 mole of NaCN, it's going to give you the same number of moles, which is 1 mole of cyanide ion. So therefore, it's correct to say that HCN is a weaker nucleophile. The reaction mechanism involves 2 steps. Yes, in fact, this reaction is known as nucleophilic addition. So I'm going to just show you the basic mechanism, how it looks like. So it looks something like this. Okay, maybe I'm just, in this case, I'll just use a R to represent the alkyl groups for this particular example. So we have a carbonyl and aldehyde. So cyanide ion will attack the electron deficient carbon's atom, break the pi bond. So that's a nucleophilic attack. Now, subsequently, we're going to follow up with a protonation, because now your alkoxide, your tetrahedral alkoxide intermediate will be protonated to form your hydroxynitrile. Sometimes we call this cyanohydrine. Cyano means because your CN, hydrine means OH. So it does involve 2 steps. The first step is a nucleophilic attack of the nucleophile. The second step is the protonation process. Now, the product of the reaction has a chiral carbon atom. Yes, if you see your product, it is a 2-hydroxybutanediol. This carbon itself, okay, let me just highlight it. This carbon itself is a chiral carbon because it's connected to 4 different substituents: your ethyl substituent, your hydrogen substituent, your OH substituent, and a CN substituent. If you can't see it like this, draw the molecules, and you know what I mean. So therefore, all the 3 options are correct. The last one, lactic acid. The structure of lactic acid is shown. So which ester might form when lactic acid is heated? Now, to solve this, actually, it'd be good if you can visualize this by yourself, but I'm just going to draw out the molecules. Hopefully, you'll be able to see a lot better. Okay, I'm going to draw another one over here. Now, to get the first ester, you notice that actually you must combine 2 esters. Right? How you know you need to combine 2 esters? Well, you just check how many carbon atoms there are. 1, 2, 3. Over here, we count, actually there are 6. 1, 2, 3, 4, 5, 6. That means you need 2 lactic acid molecules. And how do they react? Well, you undergo an esterification process. Esterification process. That means the OH over here will react with the OH over here. Whereas the OH over here will react with this OH over here. Because the carboxylic acid with alcohol, alcohol with carboxylic acid. And this will give rise to option 1 molecule. Try it for yourself. Now, for option 2, how do we actually get this species? Well, it's actually very interesting. You also need to have 2 molecules, but they actually forms a intra-esterification process. Okay, so let me just draw up the option 2 so that you can see a lot better. Okay, so this is what we have here. So now just imagine that prior to that, if you were to click this side, previously this is actually an OH and there's an OH here. You click this side, there's an OH, there's an OH here. So do you notice this whole chunk itself is actually a lactic acid. Over here is another lactic acid. So this is how we can get this molecule for option 2. For this one, it's not possible. It's not possible because you see you have a CH3, CHOH, CH3, CHOH, then it's CO. Yes, that means this H is gone, right? This H is gone. But it's gone to who? It's gone to another carbon atom. This is not possible, right? Because for esterification to occur, you must have a hydroxyl group and a carboxylic acid. So I'll be doing this live streaming more often. All right, so feel free to join this session. If there's any questions, you can always put in the chat box. Unfortunately, I don't think there are any or many participants for this session, but it's okay. I'll be posting these videos on YouTube so that you can actually look at it again. All right, so that's it for now. If you like this video, subscribe and hit the notification button so that you don't miss any of my future chemistry videos. Talk to you soon. Peace out.